So this is going to be mostly trial and error, trying to figure out what works best for everyone. So what I'm going to do is walk you through attacking some Arrhenius equation practice problems. So let's read through some stuff. I already have the answer key typed up. It's already uploaded to ECLearn, but I'm going to use this video to help kind of walk you through the answer key if you're having difficulties interpreting what I've written. So let's read through what we have here. So it says the first order rate constant K of a reaction was determined at several different temperatures in units of Kelvin. The natural log of the rate constant was plotted versus the reciprocal temperature to create the following plot. And this should make sense because if we take a look here, the first order rate constant, right, was determined at several different temperatures. Well, there we go right here. There's our several different temperatures. So 1, 2, 3, 4, 5 different data points. We were measuring K, so the first order rate constant K of the reaction was determined at several different temperatures. It's exactly what we see on our plot. So we know what the Arrhenius equation is, right? That's one way to write it. If we want to keep in mind, we also know that K equals the pre-exponential factor A, Euler's number E raised to the negative EA is our activation energy over the universal gas constant times the temperature in the absolute temperature, which is in Kelvin. You can also, you can also rearrange it mathematically, like we talked about in the slides, to look like this. So let's start with some of these problems. So it's telling us. It says using, hold on, I'm just trying to get control of the screen. Sometimes it can be a little pain in the butt. Come on. All right, because I'm in annotation mode, it's not letting me. There we go. Sorry, I'm trying to use a combination of actually three different programs at the same time. It seems like they're conflicting a little bit, but it's just going to take practice to make sure we get good at this. So we have our data, and it says using the Arrhenius equation and the linear regression shown in the plot, calculate the rate constant at 298 K. So we need to know a couple of things. So we're trying to find the rate constant K at 298 K. So part A, we need to recognize that the y-axis is plotted in the natural log of K, and the x-axis is plotted as 1 over the absolute temperature. So what does that look like? What we can see is, just like what we saw above, we have our natural log of K versus reciprocal temperature, where we had some sort of slope. This slope, this line here, and this is taken, if you want to go back in the video, it's just going to be difficult for me to keep switching back and forth, but this was our linear regression, the negative 601.5x plus 6.908. So when we look here, this is what I'm looking at here, y equals, well, y is my ln k, my x is 1 over t, ln k, 1 over t, my slope is negative ea over r, that's that negative 601.4, and my natural log of the frequency factor is my 6.908. So there's my linear regression. So therefore, I know y equals the natural log of k. Why do I know that? Again, let's take a look. The natural log of k is y. Well, that's y, right? We know my slope is equal to negative ea over r. Why? Because that's y. That's my m, my slope, right? My x is the reciprocal of temperature. Why do I know that? Again, we're going step by step. There's my x is 1 over t. My y-intercept of natural log of a, well, there it is. So I have all of this information. I can pull out all of those constants. So, again, I apologize. I'm using, like I said, a couple of different programs to do my best to get everything to flow together. So the problem was asking us what is K at a specified temperature, and that temperature was 298 K. So what can I do? Well, if I take a look here, well, it's EA over R. I have A. The only thing I really need to know is, because if I look here, the only thing I need to know is temperature, which is X, or 1 over T, to figure out Y, which is ln of K. So let's do that. It's going to bring it up. Okay, discard. So let's do that. This is what I'm trying to solve for. I already got those numbers. There's my temperature in Kelvin. Do the math out. I end up with 4.890 on the right-hand side of the equation. I exponentiate and solve for K. So I have a numerical value, but I need to know what its units are. And what we've started to see so far is when we have a natural log, and what we'll see when we get to acids and bases, natural logs and logs, you basically need to know what the units are going to be. They kind of erase them. So effectively, yeah, we have a K that is unitless, but we were informed that as a first order reaction. So we know the units must be per second or some sort of per time. You would need to know additional information to know exactly what that K is. So this is our final answer, 1.33 per second. B is asking us to answer, let's actually go back up and reread it, right? B is asking us to find the activation of the reaction. So things that we need to pay attention to, right? I've just solved for K at a particular temperature. ln of A is known, right? R is known. I'm asked to find the activation energy, or the activation energy of the reaction. We'll take a look. There it is. One equation, one unknown. We're good to go. Hold on. Still. Get me out of this. Come on. I don't know what it's doing. Why is it still in annotation mode? There we go. Let's try it that way. All right, that seems to be a little bit easier if I do it on the iPad. All right, so sorry about that. Like I said, we're working out the kinks on this one. So, what we're trying to find, and actually, let's take a look, right? We're asked to find the activation energy, EA. We could make our life harder and use the entire equation, or what we can do is recognize the only thing I really care about is right here, which is the slope, which has this value. So there's my slope, m equals EA over R. Rearrange that equation so that EA equals negative MR. All I did to do that was multiply both sides by negative R. That's a multiplication sign if you can't tell. Well, that ends up with our, go back, with this. What we can do now is just plug in our numbers, because if we take a look, well, what is my slope? Well, my slope here, the negative 106.4. Where did I get that? Well, there's my slope. Dump that in. It's a negative negative, it will be positive. 8.314, that's just my units for R. Multiply that together. There's my EA. Again, my EA doesn't have any units. So what I need to figure out are what those units, and this is a little bit more difficult. So remember what the definition of slope is, right? The definition of slope is going to be the change in y over the change in x. So what we need to do is plug in, instead of worrying about numbers, is plugging in our units. So for delta y, change in y, if I go back up and take a look here, it'd be my change in y, and my units are ln of k, and this is probably the first time we're dealing with it. Natural log and log do not have units, so they're unitless. The way I'm going to represent that is here. There's my delta y that I'm looking at. I just put the number 1 here. Why? Because it's unitless. It's something, so it can't be 0, but it has no units. So I'm going to put it as just the number 1. My units for delta x, right? If I looked at that graph I had up there, we said it was ln of k versus 1 over t. Well, if my x is the units of 1 over t, Well, that would be 1 over Kelvin. So it's 1 over Kelvin. If I do that math out, it just becomes Kelvin. Therefore, the slope m has units of Kelvin. Plug it back into this equation, EA equals negative mr. Plug in just my units. So my units for for temperature are right here. My units for R are right there, joules per mole Kelvin. What we can see is the kelvins cancel out. I'm left with joules per mole. It's exactly what the units for EA should be. EA is now 5 kilojoules per mole. So it's my final answer with correct units. The last question is asking me, let's go back up, for C, the collisional frequency factor, or the orientation factor. So again, I ask myself, what am I looking for? There's my Arrhenius equation. I am looking for specifically the collisional frequency factor, which is here, A. So let's set up our problem so we can solve directly for A. Oops, hit 3 fingers instead of 2. So we go down here. Again, we start with our Arrhenius equation. There we go, the Arrhenius equation. Remind myself what I'm trying to solve for. A. That's what I'm trying to get to. So either I need to know everything else, or, easy enough, recognize that the ln of A is equal to this number. So that's what I have here. The natural log of A equals the y-intercept. Where did I get that? Again, from that graph, ln of k over 1 over t gives me a negative slope. My y-intercept will be my collisional frequency factor, A, is right here. Let me wipe that for clean. So we can set up our equation. We exponentiate, solve directly for A. I tried going through and calculating the units for A, but long story short, A is just going to have the same units as K. So, same units as K, or the rate constant. And that actually is the end of that, of this particular problem-solving video. And if it would ever choose to end. Hold on. Oh, I gotta get out of drawing mode. Keep screwing things up. Alright, now